Here's yet another example of applying Faraday's law of electromagnetic induction, and it refers to the slide wire generator. So let's answer question A. First of all, we're told the rod is given an initial velocity, we'll say V naught, and then from there it's just released. So something like a flick or an impulse sets the rod in motion, and at some point later in time, the rod reaches this point. So as the rod slides to the right, more and more magnetic field passes through the area, and that represents an increase in flux into the page. And so current would be induced in that rod in a direction that would try to oppose that change in flux. Let me change the notation and call this lowercase l. And we'll say the rod has a mass of m. So we have to come up with an equation that expresses the speed of the rod as a function of time, right? Velocity is some function of time. So first of all, let's see if we can figure out how much force would be exerted on that rod at any given instant. So we'll start with Faraday's law. Induced voltage is negative N d phi dt. In this case, N equals 1, and the negative sign is just going to tell us the direction of the current. So in magnitude, we don't need to concern ourselves with that. So the induced voltage is equal to d dt, the product of magnetic field and area. So we've got the length as part of the area. I guess we also need some amount of width. And so the width is a measurement along the x-axis. So we can say this is equal to d dt of b times length times width. So the magnetic field and the length don't change, and we're just left with d width dt, which is the same thing as dx dt. So we have that the induced voltage is BLV. Now, that means there's going to be, according to Ohm's law, a current, and if we divide current, EMF by resistance, we get current, so we get BLV divided by R. By the way, what's the direction of that current? So there's a few ways to figure that one out. Number one, we can imagine what happens to the free electrons. So picture a few free electrons. They're all moving with a velocity to the right. By the right-hand rule, if you point your thumb to the right and your fingers into the page, your knuckles face down, so the electrons would drift downward, which means a conventional current flows upward. Another way to figure out the direction of the current is to consider that Lenz's law says there has to be some force of opposition that results on this rod. So what's the only way that I could get a force? You could use a right-hand rule and say, how could I get a force to point back to the left when I have a magnetic field that points into the page? So how can I make my palm face to the left while my fingers point into the page? Only if my thumb points upward. So we just came up with two different reasons how we could justify the fact that the current flows upward in this rod. There's actually a third method we could do. We could say as the rod slides to the right, then it opens up a greater amount of area for flux to point into the page. And if nature opposes change in flux, then the induced current should have its own magnetic field that points out of the page. And so there's a right-hand rule that says curl your fingers in such a direction that your thumb points out of the page. And again, that would be if your fingers curl around in a counterclockwise direction, which agrees with saying current flows upward in the rod. Okay, so in any case, the current is BLV, and so that force of resistance that opposes the velocity of the rod can be found. We know F equals BIL. So how about force is equal to B, and then we'll substitute in place of I, BLV over R, and then that's multiplied by L, right? BIL. So we get b squared L squared V divided by R. Well, by Newton's second law, F equals ma. So we have ma equals b squared L squared V divided by R. And now I said I'm going to ignore the negative sign because that just gives me the direction of the force, so we know the force points back this way, but in our frame of reference, to the right is positive. So this is a negative amount of force, so the acceleration is negative b squared L squared V over mr, and acceleration is the rate of change of velocity. It's dv dt. So dv dt equals negative b squared L squared V divided by mr. Now this is interesting. This is an equation that says the rate of change of velocity is itself proportional to the velocity. So I could express this equation one more way. I can say dv dt is equal to negative, and I'm just going to make up a constant, lowercase c, is negative c times v, where c would have to be equal to b squared L squared over mr. So if this is the case, we could rearrange the equation and say dv over v is equal to negative c dt, and then integrate both sides of the equation. So we're going to say at time t equals 0 is the moment that the rod was first given this velocity v naught, this impulse to make it want to move to the right. And then a force shows up pushing it to the left, and so at every moment in time as it moves farther and farther to the right, it's moving slower and slower and slower. We would expect that a velocity versus time graph, or speed versus time graph, would look something like this. It should decay away towards 0, starting with a speed of v naught, and due to this resistive force, gradually bringing it to rest. So we're going to integrate as at time t equals 0, the velocity is v naught, and then at any other random time t, the velocity has just reduced to some other value we can call v. Now, if we wanted to integrate to infinity, then this would be 0, but it's going to be difficult for us to integrate to infinity. So the left side of the equation, the solution is natural log. We get the natural log of v evaluated from v naught to v. And then the right side couldn't be any easier. We just get negative ct. So if we plug in the limits of integration, we have the natural log of v minus the natural log of v naught equals negative constant times time. That's the same thing as the natural log of v divided by v naught is negative constant times time. So we'll do the same thing on both sides of the equation. And now we get v over v naught equals e to the negative ct, which means v equals v naught times e to the, oh yeah, that's what c is, b squared L squared over mr. So e to the negative b squared L squared over mr times t. So there we go. There's our answer to part A. That's an equation for velocity as a function of time. And let's see if it matches our hypothesis. If we let t equal 0, what do we get? Well, e to the 0 is equal to 1. And so we would just have at time t equals 0, v equals v naught. And what if we substituted a very large number approaching infinity for t? Then we would have e to the negative something that approaches infinity, which is like having 1 over e to something approaching infinity, which gives us 0. So that agrees with our suspicion that the graph of velocity versus time would have this shape that depicts exponential decay. So what was the other question we had to answer? Part B. Find a way to express the total energy consumed by the resistor from t equals 0 all the way up until t equals infinity. So we agree that the induced current, maybe this has gotten a little too messy. Let's erase some of this. Okay, so as the rod continues to drift to the right, slowed by a resistive force pointing opposite the initial velocity vector, a current continues to flow in this counterclockwise direction through the resistor. So we could say something like power equals current squared multiplied by resistance, and then energy is equal to power times time. The only problem with this would be the current is not a constant amount of current. Because the velocity is decreasing, our expression for current depended on velocity, but the velocity changes with time. So how can we figure this out? Let's try a couple different methods. Power is equal to current squared times resistance. Power is equal to current times voltage. Power is equal to voltage squared divided by resistance. And energy is equal to the integral of p dt. So what would any of these expressions give us? Let's try each one. The current is BLV over R, and the voltage is BLV. So this would be BLV over R, quantity squared, times R, and that would give us B squared, L squared, V squared over R. If we multiplied current times voltage, we'd have BLV over R times BLV, which would give us B squared, L squared, V squared over R. I'm going to guess that this last expression would give us B squared, L squared, V squared over R. Okay, so no matter which way we look at it, we have an expression for power, so we could use that to get an expression for energy. It's the integral of B squared, L squared, V squared over R dt. Now B is constant, L is constant, R is constant, but we just came up with an equation that expresses how velocity varies with time. Velocity is equal to V naught times e to the negative constant times time. We can substitute for that constant later. For now, to keep the expression from looking too complicated, we'll just say it's some constant c. So we're going to take all of these values and pull them out of the integral and say that the energy is equal to B squared L squared over R times the integral of V naught squared e to the negative 2 ct dt, right? Because we have to square velocity, and this is the expression for velocity. Okay. Oh, and if we need to find the total energy consumed by the resistor from time t equals 0 to infinity, then those are our limits of integration. I guess this V naught can also come out of the integral, so we get E equals B squared L squared V naught squared over R times the integral e to the negative 2 ct dt from 0 to infinity. Now what's the integral of e to some constant times time? I think what we get is, the solution is 1 over negative 2c times e to the negative 2ct. And then our limits of integration are from 0 to infinity. 0 to infinity. Okay, so if we plug infinity in for time, or just imagine plugging in a very large number, because this is a negative exponent, then for very large values of time, we get a solution approaching 0. So we have negative 1 over 2c times 0, and then we plug in the lower bound, e to the 0 gives us 1, so minus 1. So all that does is cancel out the negative sign. So we have the energy is equal to 1 over 2c times b squared L squared V naught squared over R. Now, let's plug in for C. Let's see. Well, let's write this a little differently. This is the inverse of C times B squared L squared V naught squared over 2R. How's that? Okay, so what's C? C is B squared L squared over MR, so 1 over C is MR over B squared L squared. Ooh, I think something interesting is going to happen. MR over B squared L squared. MR over B squared L squared multiplied by B squared L squared V naught squared over 2R. Oh my goodness. The R cancels out. The B squared cancels out. The L squared cancels out. And look what we're left with. We're left with the energy is equal to 1/2 m V naught squared. Spooky.